Today I'm going to be talking about some work I recently did with my supervisors, Giovanni and Chris, and with two collaborators of ours, Romy and Rob, and they're neuroscientists, so this talk is going to have a bit of a neuroscience feel to it. Before I start, just a few words about myself. I'm a PhD student at Imperial College, finishing my PhD this summer. Most of my research is involved with computational statistics driven by problems in sort of computational neuroscience. So in particular, I work with functional MRI, which measures blood flow in different parts of the brain, and I try to decorrelate that and understand the networks that sort of drive different tasks. And, well, I use Python, which is why I'm here. So in this talk, I'm going to talk about restricted and deep Boltzmann machines. I want to try to give you guys an idea of what they are, what are the advantages and disadvantages of using these models, and I want to briefly discuss training and model selection. And I want to try and motivate all of this with an application to text mining. So just to give some context and some motivation for this work, there's tons of reasons why you might want to build a text mining model, things like information retrieval, information extraction. But actually, in the context of this work, we had a very specific motivation. So we recently did some work, which we sort of quite provocatively called the automatic neuroscientist. And the idea behind this work was to somehow try to redefine the way a functional MRI experiment works. So the way it currently works is a neuroscientist will choose an experimental task. Say you're going to watch a video. They'll then put a subject in the scanner, and then they'll observe the brain activation from that task. But actually, what the neuroscientist is interested in is a specific brain region, right? So they'll have in mind brain region X that they want to activate, and they'll have then gone into the literature and said, what are the different tasks which activate this brain region? And they'll have chosen the task as a function of that. So actually, in the traditional setting, the mapping goes from experiments to brain activation. But what the neuroscientist is really interested in is going the other way around, right? They want to choose a brain activation, and they want to optimally learn the task which maximizes that brain activation. So just to put this in context, if you think of in a commercial example, if you have a website, say you want to maximize some KPI, for example, conversion rate, you might play around with the different parameters of your website, but ultimately what you're interested in is you want to maximize that conversion rate, right? So you want to automatically learn the parameters of your website which lead to maximum conversion. And actually, the framework that we used here was developed recently in a machine learning context in order to tune hyperparameters for models. So if you think of like deep learning models, they have a lot of hyperparameters, and often tuning these hyperparameters is really difficult, but measuring the model performance is quite easy. So the framework that we used here effectively measures the performance and automatically tunes these hyperparameters. So that's a bit of the motivation behind this. And so we had this sort of setup where you had a subject in the scanner, you measured the brain activity for a given experiment, you compared that to the target brain region, and then you use that to sort of redefine the experimental paradigm that you showed the subject. And you sort of iterated this in real time. And so we did this for a very simple experiment, which contains sort of audiovisual cues. And we found it to work, and that we were quite excited by that. And so we thought, great, it sort of works for an audiovisual task. What if we could be more ambitious, and instead of just searching one audiovisual task, we could search 20 tasks? Or what if we could be really ambitious, and we could search through all the tasks ever proposed in the sort of neuroscientific literature automatically in real time? And sort of this is what led us to sort of collecting a bunch of neuroscientific papers and building a neuroscientific corpus, and then trying to sort of study that and sort of embedding that in some high-dimensional space, which would make it easy to search over. So fortunately for us, we're not the first people to think about this. There was a Nature Methods paper in 2011, which did something similar. What they effectively did was they scraped a bunch of neuroscientific papers. So they went across and collected the text for 10,000 neuroscientific papers. And along with the text, they also collected the brain regions that were reported to be activated in the corresponding papers. Right? So they have this rich data set where, on the one hand, you have the text, the vocabulary, which describes the experiment that was done in some scientific study. And then you have in some standardized space the brain regions that were reported to be activated by that study. And if you want to play around with this data set's freely available at neurosynth.org. So in this work, we didn't actually use the full text. We just used the abstracts for the various papers. And there was two reasons for this. First of all, the abstract length is much less variable. It's much more homogeneous across papers. And that sort of made learning a little bit easier. It also sort of reduced the size of the vocabulary because there was fewer words. And second of all, we sort of hypothesized that the abstract would contain most of the information about the about the task that was performed, right? So it would be like a concise description of what the paper was about. So here's an example entry of what we were working with. So here you have an abstract for sort of a human episodic memory task, which is a sort of a verbal associative encoding task. So this is what we would be feeding in to our algorithm to try and learn a distribution over the text. So given sort of 10,000 abstracts of this form, we had sort of two overarching objectives, right? The first of all was to try and sort of cluster all these documents together so that you could put papers that sort of described similar experiments in similar clusters so that you could search over them efficiently. Inherent in any clustering task is some measure of similarity or some measure of distance. And actually, defining robust measures of similarity or distance across text is quite tricky. But it's far easier to do this across vector spaces, right? And there's a whole wealth of knowledge on how to define measures of similarity across vector spaces. So the main objective of this work was to somehow learn a low-dimensional vector representation of each document which captured the semantic regularity of each of the text, right? So what we effectively wanted to do was to take each abstract for each paper and sort of embed this in some high-dimensional vector space which captured the semantic regularities and what the task that this abstract was describing. And then once you have everything in a high-dimensional vector space, you can sort of leverage the vast field of work in ML and all sorts of algorithms which are well suited to dealing with continuous spaces. So those were the sort of two main objectives of this work. And we did this using Boltzmann machines. So I know it's a Sunday afternoon, and before I get stuck into discussing details of the model, I wanted to give you guys a taster for what we were able to achieve. So on the left-hand side here, what we have, each dot corresponds to a document in our corpus. And what we've done here is effectively each document has gone up through the Deep Boltzmann machine, and it's been embedded in some high-dimensional vector space. In this case, the vector space was 50-dimensional. We've then reduced the dimensionality of this to 2 dimensions using TSNE, which is a stochastic neighbor embedding algorithm. Basically, what it tries to do is it tries to find a 2-dimensional embedding of the high-dimensional space where the distances between the points are sort of preserved. We then ran some really simple clustering. So in this case, it was k-means clustering to try and learn some clusters over this embedding. And what you see on the right is the associated brain activations associated with some of these clusters that we learned. Now, if the clusters were totally meaningless, the brain activation maps that you would see on your left would be sort of homogeneous across the whole brain. But actually, it turns out that some of the clusters we've learned are able to specialize on very specific brain regions. So for example, this cluster here clearly picks up the motor brain region. So going back to our sort of experimental design context, if the neuroscientist said, I want to really activate the motor brain region, we might say, great. We have these papers corresponding to cluster number 6 here. You might want to study the abstracts there and search those tasks described there because they're going to lead to high activation in the brain region. Similarly, we have the amygdala, which is highlighted here by cluster number 3. And then exactly the same way, if the neuroscientist was to say, I really want to target the amygdala, we would say, great. Look at the documents in these clusters. So in the remainder of this talk, I'll sort of describe how we got to this plot. So I want to start by talking about restricted Boltzmann machines, which are sort of a special case of deep Boltzmann machines. And before I sort of describe them, I just want to sort of highlight what the advantages of Boltzmann machines are and how they're slightly different from traditional neural networks. So Boltzmann machines, as opposed to traditional neural networks, are generative models. So they're actually looking to learn a distribution over your data. And this is slightly more difficult, right? Because you need to model all your data points well. One of the advantages of learning a generative model is that once you've learned this distribution of your data, you can then sample from it, and you can effectively dream up new data points, and you can generate more data. The reason people like Boltzmann machines is because they're fully unsupervised. So this makes them suitable for sort of pre-training neural networks. So if you imagine a context where you have a small set of labeled data, but you have a large set of unlabeled data, then you can leverage this unlabeled data, learn the distribution of over this unlabeled data using a Boltzmann machine, and then use the weights that you've learned as a sort of warm start for your neural network, and then fine-tune those using backpropagation. However, there's 2 sort of key disadvantages to Boltzmann machines. The first is that training is not straightforward. So since we're dealing with sort of graphical models, the training isn't just a case of backpropagating through the algorithm, and it's a little bit more complicated. And secondly, model selection and model comparison. So if you remember, we're in a totally unsupervised setting, so model selection needs to be based on some sort of validate out-of-sample likelihood. And actually, this is really complicated in Boltzmann machines because there's a normalizing constant, which is a bit of a headache to learn. So those would be, I would say, the two main disadvantages. So to give you guys an idea of a Boltzmann machine, of what a restricted Boltzmann machine is, it's a special case of a general Boltzmann machine. So if you assume we have some sort of vector of visible units here, for now, let's just assume they're binary. So just treat these as if they were pixels in some sort of black and white image. And you wanted to learn a distribution over these binary random variables. In a Boltzmann machine, you hypothesize that this distribution is driven by or related to some latent hidden units. So in addition to your visible units, you also have some hidden units which sort of determine this distribution. And in the Boltzmann machine, you assume that the distribution is sort of specified by pairwise potentials across these units. So each of these edges effectively determines a sort of piecewise or sort of statistical dependency across the visible and the hidden units. And in a Boltzmann machine, effectively, each visible unit has a conditional dependency on every single other unit in your model. And what this means is these models are really expressive and really flexible, and they're able to learn sort of really complicated distributions, but they're also really difficult to train because you have all these dependencies to account for. And so the idea in a restricted Boltzmann machine is that you restrict the graphical structure of your model. In particular, you sort of enforce the structure to be bipartite. So you force all these edges between visible units to be 0, to be removed from the model, and all these edges between hidden units to be removed. And so effectively, you only have edges from visible to hidden units and vice versa. And as we'll see, this is going to really simplify training and inference on these models. So restricted Boltzmann machines are sort of models that came out from the statistical physics literature, and they're what's called energy-based models. So each of these pairwise potentials is parameterized by some real number. And effectively, what you can think of this number here as being, if this number is positive and this visible unit is on, it's going to really encourage this hidden unit to be on, and vice versa, right? So these models are entirely undirected. So if this number is positive and this hidden unit is on, this guy's going to be encouraged to be on. And so learning a restricted Boltzmann machine effectively boils down to learning these set of parameters. And what you effectively want to do is sort of maximize some energy function. And so in the context of training, we only have the visible units. So what you want to maximize is the likelihood of the visible units after you've marginalized out these hidden units, right? So you sort of sum over all the possible hidden units, and you want to maximize the likelihood of your visible units. Now, because of the bipartite structure, you can actually calculate that likelihood analytically or up to a normalizing constant. And that's what makes sort of training feasible. So as I mentioned, this bipartite structure leads to a few sort of desirable properties. The first of them is that the visible units or the hidden units are conditionally independent given the other units, right? So what I mean by this is given a set of hidden units, each of your visible units is conditionally independent. So if you wanted to sample your visible units given the hidden units, all you would have to do is sample each of these guys independently. So instead of having to sample a vector here, you just have to sample a bunch of univariate random variables. And so that makes life a lot easier. And it's the same is true vice versa. Furthermore, each of the distributions of the visible units we know analytically. So we know that each of the visible units given your hidden units will be a Bernoulli random variable with a parameter specified by the sum of the inputs passed through some sigmoidal function. So actually sampling the visible given the hidden units or vice versa is really easy, and we can do it in closed form. And actually training restricted Boltzmann machines and deep Boltzmann machines just boils down to doing this a bunch of times in a special way. So just to make this perfectly clear, if you wanted to do this in Python and you had some vector of hidden units, all you have to do is take the dot product with your weights matrix and then pass that through some sigmoidal function. And all you do is then sample a Bernoulli random variable with that activation function. So in Python, you can sort of sample the visible given the hidden units or vice versa in just 2 lines of code. So training. So like in traditional neural networks, training proceeds via sort of maximum likelihood and stochastic gradient descent. But as I said, the problem is this derivative is no longer available in closed form like it is in backpropagation. And the reason for that is we're trying to learn a graphical model where the hidden units are actually random variables. And so this derivative actually boils down to the sum of two expectations. The first is a sort of data-dependent expectation, and it's the expectation under the distribution of the hidden units given the visible units. Now, in a restricted Boltzmann machine, we know this distribution in closed form. So actually, getting this expectation and getting an unbiased estimate of this expectation is really easy, and we can do that analytically. The second expectation, which is the data-independent expectation, is a little bit trickier, because this is an expectation over the joint distribution of the visible and hidden units, and we don't know what this is. So this is where sort of the headache comes in, and this is where we need to approximate the derivative. So this guy can be done analytically, and we have an unbiased estimate, but this guy must be approximated using sort of Markov chain Monte Carlo methods. So just to reiterate, the data-dependent expectation we can calculate really easily. The data-independent expectation we need to sort of approximate using Markov chain Monte Carlo. So the approach that is typically used is sort of to exploit this conditional independence structure, and you sort of just sample the visible given the hidden units and the hidden given the visible units, and you iterate this k times. And as k goes to infinity, you approximate the joint distribution exactly. But of course, no one has time to let k go to infinity. So actually, in practice, you just often set k equals some number. Often k equals 1 is used. And empirically, it's been shown to perform fairly well. But actually, people that know about MCMC will tell you this is a very bad approximation to that expectation. So just to sort of show you how you would do this in Python, the data-dependent expectation can be calculated in closed form really easily. So all you do is you sort of take some visible units, which is your data, you feed that up, you sample your hidden units, and this is your sort of data-dependent expectation. Then to learn your data-independent expectation, you just sort of iterate in this Gibbs sampling procedure. So here I've just done it once, but if you were to do this sort of within a for loop k times, you'd effectively get a better approximation. And then you just take the difference of these two terms, and that's the direction of your gradient, and you just take a small step in that direction, and you iterate. So restricted Boltzmann machines are unsupervised learning methods, so it's especially important to sort of try and avoid overfitting. It's also the case that they're unsupervised, so you have to be extra careful to avoid overfitting. So in the previous talk, we had some slides showing the likelihood in the test error and the validation error, and that's certainly one way you can sort of avoid overfitting. Once these two start to diverge significantly, you should probably stop training because you're overfitting. But the method that I used in this work to try and avoid overfitting was just drop out. And what this effectively boils down to is you just sort of, at training time, randomly select hidden units to remove from your model. And what this effectively does is it encourages the hidden units to be robust and not sort of depend on the activations of other hidden units. Another way of thinking of dropout is that you're learning an ensemble of neural networks. So since you're randomly dropping out different guys, you're sort of learning different neural networks with different number of hidden units at each iteration. And then at prediction time or at learning time, you sort of put them all together. So it's a bit of an ensemble of neural networks. So far I've been describing Boltzmann machines for binary random variables. But of course, this work is about text. So we need to sort of extend that to text. So a really naive way to model text is to treat it as sort of a binary random variables, right? So if we think, for example, the sentence, the ability to bind information, so on, you can model this as binary random variables by using an incidence matrix. So for example, this vector here would be a 1 because ability is the second entry of that sentence. And then all other entries in this column would be 0. And similarly, these two entries would be 1 because bind and information are the third and the fourth entries for that matrix. The problem with modeling text in this way is that it's incredibly wasteful, right? Each column only ever has one non-zero entry. And moreover, each of these guys is only really going to be activated when, say, for example, information is the fifth word in your text. And that might not happen that often. The other problem is that a number of parameters explodes, right? So here you've described some document as an incidence matrix where the number of rows is equal to the number of words in your vocabulary, and the number of columns is equal to the number of sort of words in that document. And so you have tons and tons of visible units, and each one of these visible units is connected to all your hidden units, right? So the number of parameters really explodes quite quickly. And so this is quite a wasteful way of modeling text. So in this work, we sort of took a more parsimonious approach. We sort of just modeled the word counts. So as opposed to modeling word location, you sort of just forget about the order in which the words occur, and you just try and model the word count. And so each visible unit is no longer a matrix, but it's just a vector. and sort of the ith entry is the number of times that word occurs in your document. So, of course, since we're now modeling word counts as opposed to binary random variables, the distribution of our visible units is no longer binary, but it's multinomial. But actually, all that really changes is the conditional distribution of the visible given the hidden units, which now will follow a softmax distribution. All the other properties of training the restricted Boltzmann machine sort of remain unchanged. And actually, more generally, this is true for sort of any exponential family visible units. So you can sort of play around with different classes of visible units. So to move on to deep Boltzmann machines. So the idea in deep Boltzmann machines is you continue to propagate this bipartite structure upwards, right? So in a restricted Boltzmann machine, we just had one layer of hidden units. Here we sort of have an additional layer of hidden units on top of that. And what the idea behind this is, this first layer learns sort of an initial approximation or a distribution of your data, and this second layer then learns an additional distribution over your first layer. And so you're able to learn sort of high dimensional or really complicated representations of your data. As before, you have sort of an energy function, and each of these edges is parameterized by a weight. So all you're basically trying to do is learn these weights and these weights. And again, as before, we sort of proceed via maximum likelihood. The problem is the derivative of the likelihood is again the sum of a data dependent and a data independent expectation. But now neither of these guys is available in closed form, and both of them are quite difficult. So in the case of the data dependent expectation, you have to the expectation is over the distribution of both layers of hidden units given your visible units, and you no longer have access to this in closed form, right? And so the approach that people typically take is to use variational inference. And basically what this boils down to is you say, OK, I'm just going to assume each of these guys is independently Bernoulli random variables. And I'm just going to try and learn the parameters of these guys that closest approximate the true joint distribution or the true conditional distribution. And what this basically boils down to is you say, OK, the ith unit in my first layer is going to be Bernoulli with some parameter mu, so some probability of being on. And the ith unit in my second layer is also going to be Bernoulli. And you sort of iterate these parameters and try and learn the parameters and sort of minimize some distance to the true conditional distribution. And what it basically boils down to is you just basically iterate these two equations up until convergence. Then in the case of the data independent distribution, we have to learn the joint distribution over these three layers now, right? And so again, we sort of follow the same philosophy, and we sort of use Markov chain Monte Carlo. But as opposed to sort of just sampling up and down sort of one time, the approach that is typically advocated is to sort of keep a sort of a bunch of particles whilst you're training. And in each iteration, as opposed to starting the Markov chain from scratch, you sort of iterate these m particles up and down your hidden network. The idea here is that if the weights in your network are sort of changing at a slower rate than these particles are approximating this joint distribution, then you're going to be able to get a good approximation to the expectation of interest. So the objective function in deep Boltzmann machines is highly non-convex. And like all methods in deep learning, initializing the parameters is actually really important. And so the way deep Boltzmann machines are typically trained is you sort of pre-train your weights, and then you fine-tune them using the methods I just described. So in this work, we sort of pre-train the deep Boltzmann machines by, first of all, learning a restricted Boltzmann machine over the visible units, and then sort of propagating the data through that and sampling these guys, and then treating samples from the first layer as visible units and learning an additional restricted Boltzmann machine on top of that. And then you do some sort of minor adjustments to the weights, and those weights can be used as a sort of starting point for your network. So that was what we did. Now to just sort of describe the results that we got. So we sort of trained a two-layer deep Boltzmann machine with 50 binary random variables in each layer. And then pre-training was done with using contrastive divergence. That basically means I took one step at each iteration of estimating my data independent distribution. And I used dropout with some probability with a 1 in 10 chance of dropping out the hidden units. And so just to remind you what the data was, it was abstracts for about 10,000 scientific publications. The average length of the document was about 80 words, and the vocabulary was 1,000 words. And so first of all, the first thing we can do is we can sort of pass each word through the deep Boltzmann machine, and so represent each word as some sort of high dimensional, in some high dimensional space. And then over these sort of vector representations of the words, we can just run some really basic clustering. So here we just ran k-means, and then I'm just showing you here some clusters which we've learned. So for example, the first cluster, we have sort of memory retrieval, the hippocampus, which is a brain region associated with recollection. The second cluster sort of corresponds to sort of language. We have a final cluster down here, which corresponds to sort of pathologies and disorders. And so you can see that the representations that are being learned over words make some sense. Again, we can take this sort of representation of words and try and sort of map it down onto a two-dimensional space, which is what we have in sort of the top left corner here. And if you zoom in to some of these regions, you can see that there's sort of like semantic meaning in the representation, right? So for example, in this corner here, we have the amygdala and words like emotion and empathy, and so this sort of corresponds to the emotional coordinates. Down here, you have like recollection and retrieval and encoding, and over there, you sort of have words to do with like aging and development. The other thing you can do to sort of make sure that you've learned a reasonable distribution over your data is you can take a word, pass it up through the network, so into the second hidden layer, and then come back down and see which words are sort of highly activated. So in this case, for example, we put the word memory in as input, went up through the network and back down, and these are the words that sort of had highest probability density, right? So I should point out that working comes out here because working memory is a really big thing in neuroscience, and this was a neuroscience corpus. If you were to train this on a different corpus, I would not expect working to be associated with memory. And you can see that sort of the words that are being returned sort of make some sense, right? So if you put in face, you get facial, faces, face. If you put in disorder, you get patients and a bunch of disorders. So it's learned a sort of fairly reasonable distribution over the data. And then finally, another thing that's sort of exciting is that these hidden units appear to be somewhat discriminative, right? So if you just flick one of the hidden units on and then work your way down the network, you can see which are the words which are sort of associated with this hidden unit. So for example, if you just flick the fourth hidden unit on, you get words like younger, older, aging. Those are the words that are sort of most activated by this unit. If you sort of turn the 38th unit on, you get words like reading, language. So the units appear to be associated with sort of specific tasks. And finally, we get to the picture I showed you at the beginning, where here we have all of the documents that have been sort of put into this high-dimensional space, and then we've sort of tried to shrink that back down to 2 dimensions, and then we've run some really simple clustering on that. So that's all I have. Thank you very much. Any questions?
Thanks. It was a great talk. In the previous slide, when you were showing one back.
This one?
Yeah.
Yep.
So all these units are from the first layer, right?
So what I've done here is I've flicked on a unit in the top layer, and then I've then propagated down. So I sort of flick this unit on, for example, and then all the other units are off, and then I can sort of sample these guys conditional on just this guy being on, and then sample those guys.
So just wondering if you tried switching on only units from the lower layer and see if there is like this difference that you would expect. That
then just
first layer
these
learns
guys?
something
Well,
simple, and then
I guess these models, they're all undirected, right? So all these edges are undirected. So I would expect similar things to happen. I haven't actually tried. You mean just switching on a word, for example, right?
Yeah. So you mentioned that the first layer learns simple features, and then the next layer learns sort of more complex things.
Well, that's like the idea, right? I can't prove it. Yeah.
A couple of slides ago, you had I put in some words and some words come out. Can you go back to that one? Yeah, there it was. It was one slide.
One?
Yeah, there.
Yep.
So obviously, I don't really understand how this works because I'd think, are these in order?
Yes. So for example, if you put in memory and you work your way up and down the network, then you get basically a distribution of your words, right? So memory was the most strongly associated word.
With memory, yeah. So why is face not the most strongly associated word with face?
Yeah. So it's not always the case that the same word should be the most associated with itself.
Because I'm the most strongly associated person with myself.
Yeah, you're right. I guess I don't really have a good answer for you for that. Ultimately, the way this training has been done is it's been based on a sort of a noisy gradient. So I guess if these words sort of occur together sufficiently many times and you're only approximating, you're only getting like a noisy approximation, then it could be that this is just noise. Yeah, I mean, I guess this is just to sort of reassure you that you're learning a reasonable distribution of your words. And I would only really expect the words to sort of be roughly in this area. I wouldn't expect it to be the number one word. And the other reason for that is because for each word, I didn't show it in slides, but you also learn a bias vector. So words that occur really frequently will have a high bias vector because they're more likely to be switched on. And so, for example, words that don't occur that frequently will have will be sort of switched off because they're not likely to occur. And so, for example, I guess here with mode, the default mode network is a sentence that occurs really frequently. So this sort of makes sense to me, but also the words network and default probably occur much more frequently than mode, and maybe that's why that's happening there. That would be sort of my initial guess. Yeah.
Sorry. The faces and facial are all the same word, essentially, whereas social doesn't have many synonyms. So that's probably why the weighting's been split amongst 3 rather than just
right.
one.
Yeah.
Okay, if there are no more questions, please thank Ricardo.